doing the first, I should say, or this chapters 1 through 14 for fall semester 2022, and this will be the lecture, introductory lecture. So again, the textbook is this Giancoli. This is the 7th edition. 6th edition is perfectly okay too to use. If they have a newer edition, that's fine. It doesn't change. The textbook itself is not really required, except it is very handy to have textbook. So I strongly suggest having it. So this first chapter for this course is an algebra-based course, which means you should feel comfortable with solving algebraic equations up through quadratic equations, basic trigonometry, including being comfortable with sine, cosine, tangent, and being able to scientific notation, prefixes, which we'll get into in chapter 1, and being able to solve problems. All right, that's the main thing of physics, is being able to solve problems in the real world. So what we'll be getting into is a little bit nature of science as far as what the basis is. The problem is science is all based on observation, and from there you take measurements, you take data, you come up, you observe the universe as it is, and then try to hypothesize why things happen, or understanding, like gravity. What makes gravity work? Is it as originally was thought, that things seek their own level, whatever that's supposed to mean? So you had earth, water, air, and fire, the 4 elements. Earth was heavy, water was floated on the earth, air floats on the water and land, and then fire rises up from there. All right, we know that's far too simplistic a method of that. So the question, we eventually came up with the idea of gravity, based on many observations, how things fall. You make observations, you collect data, you make a hypothesis, and then after collecting enough data and making a model, you come up with a theory, which then can be used to explain stuff, and then you use the theory with some experiments that you try to predict will happen based on the theory. So a theory has to be a mathematical type of model to some extent. It can't be just some sort of ad hoc thing. Well, gravity works because things fall down and things like that. All right, it took until Galileo, Newton, and then eventually Einstein and others developed the theory of gravity, which is based on law of gravity, how things work. So physics really is the basis of everything. The other sciences, earth science, geology, biology, chemistry, are all based on physics. Right? You're not going to understand chemistry unless you know basic physics, including quantum physics. You're not going to understand biology unless you understand basic physics as to how things can develop, evolution, and those things. So that is what the basis of this course is going to be, and it applies to all sorts of applications. So I will be applying this course during the semester for different areas, because most people taking this class are biology majors, chemistry majors, earth science majors, and so on. So what we're going to be getting into a little bit will be, first start with measurement. All right, we take a measurement with a ruler. I got a nice picture here of it. All right, you measure that distance, and all right, how accurate is that measurement? All right, the width of that board, all right, appears to me to be about 8.8 centimeters, or this would be 88 millimeters, or this would be 0.088 meters. All right, how accurate is that number? There's a couple things about it. You have a curved board. The board is curved at the end. You also have your own eyesight. How are you lined up on the ruler precisely? So this could have an estimate. You know, it could be 8.8, it could be 8.7, or it could be 8.9. So we would report this number as 8.8 plus or minus 0.1 centimeters. All right, so this implies the accuracy of this number. All right, now we could do this much more accurately. So let's say the width of classroom, all right? I can't show you right here, but the width of this classroom is about 10 meters, all right? So just eyeballing this classroom from one side to the other side, it's normal laboratory classroom, is about 10 meters. So if I was to pace it off just by walking it, I would say this is 10 meters plus or minus 1 meter, all right? Because if I just pace it off, I mean, if I just eyeball it, it's about 10 meters plus or minus 1. Could be 11 meters, it could be 9 meters. All right, this is an accuracy of about 10%, which is probably about as good as I could do anyway on this. All right, if I was to measure this with a meter stick, all right, and I have measured this out, and the width of this room using a meter stick turns out to be 9.75 meters. And all right, the accuracy of this, all right, I'm just using a meter stick, kind of lining it up 1 to n. So the accuracy of this is probably no more than about 1 centimeter. So this would be plus or minus 0.01 meters, or this could be reported as 975 centimeters plus or minus 1 centimeter, which is pretty good, all right? Now part of this is my accuracy. We'll get into significant when we get to the end of this. All right, now we're down to about accuracy of 1 part in 1,000. So now this is about 0.1%, all right? Now, that might be fine. Measuring it this way might be great for, you know, just ad hoc measurement, but in a real construction project, you can't have it so you have a gap of a centimeter at the walls, right? You need things to be precise. Now, how precise we could see. Now, you can do what I have now nowadays. You have laser precision, laser measurements. All right, you can use a laser to actually measure the width of the room far more accurately. Now, if I use a laser, I could get this. I didn't actually do it, but on the laser, it could be 9.7513. All right. So this would be to the nearest, this would be centimeter, 1/10 of a centimeter, 100. So this would be a millimeter, so it would be accurate to within 1/10 of a millimeter. So this would be accurate to within this 1/10 of the smallest increment here. So this would be 9.7513 plus or minus 0.0001 meters. All right, which would be implying an accuracy of 0.001%. All right, this is 1 part in 100,000. So if I look at each of these measurements, they're all ones I have here, this one, and this one. All right, my accuracy then leads to how I did it, making sure my device is calibrated. This particular ruler, part of the problem might be is it could be inaccurate because the end is worn down. Now sometimes you have rulers where a piece has been cut off. Well, you could be very accurate, but you're going to be extremely you're going to be incorrect. So you have to make sure your device is calibrated correctly. You could use a laser measurement device, but if it's not calibrated correctly, you could say it's 9.2136 meters, but then be off by half a meter because something has been measured wrong. Right? I used to do course calibration for road races, and we'd have the same thing. You have an incorrect calibrated device, so you have your measurement very precise for, say, a 10K road race, but it's been done wrong. So you have it accurate to 4 decimal places, but it's incorrect. So it's basically useless. So you have to make sure it's repeatable, checked, so that it's done right. So if we look at this, we could look at what we call significant figures. And in this case, the accuracy gives us how accurate a number is. So for the first one, 10 plus or minus 1, this is what we call 1 sig fig, right? Because it's 10, so it's about 10, 1 significant figure. This one has 1, 2, 3, so it's 3 significant figures, right? And that implies our accuracy. The bottom one has 1, 2, 3, 4, 5 measurements, so that is 5 significant figures. So that's the accuracy of this measurement. Now, you might think, oh, it's just a small number. Look at that, it's got 4 to 5 decimal places. All right, now the problem with that, you have to be careful, because what you want to do a lot of times is a measurement needs to be, if it's between 1 and 10, it's not going to be a problem because you just count the significant figures. All right, so let's try something else where it could be a little confusing here. And so, all right, let's do an example. Let's take let's say the width of this paper. All right, now let's do that. Let's do the width of this. Let's do that. Let's do the thickness of this paper. All right, thickness of this paper. All right, now it's very thin, and if I was just to eyeball it, it might be, how many pages? I'd estimate that's a millimeter. From there to there, let's say 20 of them going to there. So this would be, say, 20 pages make pages is 1 millimeter. All right, So that'd be approximately, so to get it the thickness then, we take 1 divided by 20, which would be 0.05 millimeters, which would be 0.005 centimeters, which would be 0.00005. Let's see here. You get it? Yeah, you move it over 1 more to get that. Move over 2 more meters. All right. Now that's a very small number. And you might think, oh, from before I have this is 5 significant figures. Well, here, this is, well, look at all the number here. 1, 2, 3, 4, 5, 6. So you should say, well, there should be 6 significant figures because it's so small number. No, it's not. What we have is a very small number with a very big inaccuracy, because this could be, who knows what this number would be. I'm just kind of winging it as I go along. So this is could be anywhere. This is just a very rough estimate. So if I write this as scientific notation, that'd be 1, 2, 3, 4, 5. That would be 5 times 10 to the minus 5th meters. This then is 1 significant figure, because all I have is 5 times 10 to the minus 5th. So you write this in scientific notation. If you move it to the right, that's going to be negative. If you move it to the left, it's going to be a positive exponent. So another example like this might be the number 300,000 or 300 million meters per second, which, if you know, is approximately the speed of light. If we move this over 1, 2, 3, 4, 5, 6, 7, 8, this is 3 times 10 to the 8th meters per second. All right, that is the speed of light. This is also 1 significant figure. Now, while we're on this, speed of light is actually not anywhere near. It's known far more accurately than that. If I can get that, here we are. All right, so, but based on accuracy and more precise measurements, the speed of light, that's a very approximate thing. That's what I use a lot of times, is 3 times 10 to the 8th. It's a very close approximation. It works perfectly well. But the actual speed of light, based on National Institute of Standards in Boulder, Colorado, the actual speed of light is 299,792,458. So if we write this in scientific notation, this would be 2.99792,458 times 10 to the 8th meters per second. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9 significant figures. That is the accuracy of that number, right? So if you write it in, if you always write it in scientific notation, then the numbers here will give you that accuracy in significant figures. So our standards, all right, length is known to about a fraction of a billionth. Time is known to a fraction of a billionth. Because for GPS to work, so know my location here to within a few feet, you have to use extremely accurate clocks. You gotta know distances. There's a whole lot that goes into it as far as that's concerned. So this idea of scientific notation, significant figures, is extremely important. Now, while we're still on this, significant figures can be very important, but let's say I wanted to know the area of this room. This lab room is basically a square. So now I got my measurement with the laser, 9.51. Let's say I measured it 9.513 meters in width, and the length, I did that with the laser, I finished it, did it, now I did the length, and I got that to be 8.7. Oh, let's see, what was my number before? 9.5134, let's do that. All right, this has 5 significant figures. $8.75. All right. Now, if I was to then calculate the area of this thing, all right? Area is length times width. Let me get my calculator. All right, this has 3 significant figures. So if I multiply the area here, 9.5134 times 8.75, I get 83.24225 meters squared. All right, now this has 1, 2, 3, 4, 5, 6, 7 significant figures. Well, that's pretty amazing. So I multiply length times width. Again, area has 7 significant figures. Is that correct? No, because I measured this side extremely accurate. I measured this one a little less precise, and therefore the area, the accuracy is based on weakest measure. So in this case, my number here is 3 significant figures. This is 5, so my answer can only have 3 significant figures, so 83.2 meters squared. All right, that's the accuracy of that number. I mean, you might be able to push it a little bit to 83.24, but that would be it. Generally, it should be that, all right? So the accuracy in measurements when you're adding. So even if I measured half the room to extreme accuracy, the other half incredibly inaccurately. So let's say I measure the first half of the room with a laser and I get 4.7534, and the other half, so I measure the width of the room, by half, this is 4.7534. The other half, just with a ruler, I get 4.73 meters. All right, if I add them together, right, I get 9.4834. This has 5 significant figures. This has 3, but my answer can only have 3. So I'd report this as 9.48 meters, all right? So everything has to be done to the same precision to do that, to have that to be true, all right? All right, so last thing here we're going to be doing, I'm not going to do any unit conversion today. But the last thing we'll be doing are prefixes. All right? So prefixes. Or scientific notation, and there's a whole bunch. If you look in the text, there are lots and lots of units. You go all the way down from up to 10 to the 24th, down to 10 to the minus 24th. The only ones we're going to be dealing with are standard. I'll start from the top. So if you have tera, let's see, terabyte, terameter, which is like TM. This is 10 to the 12th meters. Giga meter or giga kilogram or gigasecond. This would be GM, which is 10 to the 9th. Mega meter or mega whatever. MM, 10 to the 6th. And kilometer, right, which is KM. We actually use a little k then, which is 10 to the 3rd. And we use just meter, 1 meter, just M. So that's 10 to the 0. Which is 1, and centimeter, which is 10 to the minus 2nd meters, millimeters, and we're using little letters, 10 to the minus 3rd, micron, little Greek letter mu, M, 10 to the minus 3rd, which is 10 to the minus 6th meters, 1 picometer, which is the last one we're going to, nanometer, I'll go pico, which is 10 to the minus 9th meters, and then picometer, which is 10 to the minus 12th. All right, so these are all different by factor of 3, with the exception of centimeter. So these are all the units we're ever going to use for this class. And that's in the textbook. Don't worry, there's things you go way up, very small, as far as that's concerned. So that is in the class. So also while we're at it, make sure you never forget a unit. So if you make a measurement, I measure this room, say it's 9.5134 meters, all right, meters, all right? People sometimes write an answer, they forget what it is. It's not 9.34, it's in meters. All right, there was a Mars Pathfinder, not probably Pathfinder, but the Mars orbiter launched in 1999. One reason why it crashed is because prior to 1999, engineers would always use English units, pounds, feet, seconds, for whatever, because that's what they use. I mean, we measure a house, we do it in feet and inches. Engineers, scientists were using metric system. Well, you know, when you're writing something down, you kind of don't, you know what the units are, you don't bother with it. Particularly if you're entering a computer, you can't really enter it in with the units in there. If you're just having a number, you're gonna do a calculation, you can't have that in the calculation. Well, the problem is they mixed up, and what happened is the engineers thought it was in one unit, scientists thought it was another unit, and it ended up coming in too low in orbit, and a $125 million satellite was lost orbiting Mars just like that. So nowadays, everybody at NASA uses metric units. So you gotta be careful, don't report an answer without the units. Don't just put down this and assume we know what you're talking about, all right? I mean, this would be perfectly valid if you had it as 951.34 centimeters. That's perfectly fine. Or you could do it in kilometers for all I care. All right? So if you did this in kilometers, you'd move it at 1, 2, 3. This would be 0.0095134 kilometers. Width. That's the width of the room. Again, 5 significant figures, 5 significant figures, 5 significant figures. So that's chapter 1 of physics